Today we're going to talk about frequency, and especially instantaneous frequency. I've been talking about instantaneous frequency for about 15 years. Previously, there are people talk about instantaneous frequency, but the way they talk about it is slightly different. Instead of real instantaneous frequency, they define it by Wigner-Weil distribution. Wigner-Weil distribution actually is an integrated instantaneous frequency. At any instant, there's only one frequency. We will discuss that at the end of the course. I dislike that, and I think that's illogic. You can have a very complicated sound, for example, an orchestra. Now you ask the question, what is the instantaneous frequency at a particular moment? A trained or even an untrained ear can hear many different sounds. You can hear violins, you can hear drums, you can hear horns, you can hear all kinds of instruments. Actually, a good conductor can pick up the misplayed of a piece, of any piece. But if you define instantaneous frequency as only one value, that means the average of all the sounds, then all the details, all the nuance are all lost in these averaging processes. Yeah. So start from the instantaneous frequency that I start to talk about in a different way, people start to take notice. For example, in September, at the University of Minnesota, we hold what we call a hot topic conference. The hot topic conference actually is conducted by the Institute of Mathematics and its Application at the University of Minnesota. The title of the conference is Instantaneous Frequencies and Trends for non-stationary and nonlinear data. Yeah, at the conference, this by invitation only, there are about 50 attendees. And after the conference, University of California at Los Angeles, UCLA, there's a big institute called IPAM, Institute of Pure and Applied Mathematics. And they pick up this theme and will organize another workshop in the spring, in the beginning of 2013. So everybody should prepare to attend that meeting in Los Angeles. Yeah. And that conference, instead of called instantaneous frequency, is called adaptive data analysis. Yeah. In fact, I find that when I search for frequency, and I find other information, including quantification of nonlinearity. Now let's see. The word instantaneous frequency has been around for a while, and it actually invokes very different reactions. For example, in 1953, Shekels wrote in IEEE magazine, they say the term instantaneous frequency should be banished forever from the dictionary of communication engineer. Who use frequency the most in the scientific engineering community? Communication engineer. They always broadcast with a given frequency or either AM or FM. Okay, they all depends upon frequency. F stands for frequency, and this gentleman, I should look up his background. He must be very influential back in the 50s. He said the word should be banished, should never be used, should disappear from the dictionary. Yeah. It's worse than just burning the books. It's actually take away even the name. And then that's the engineering point of view. Now we can brush that away. So engineering don't know better. This is a mathematician. He wrote a book on Hilbert transformation, a distribution-based Hilbert transformation. And in there, he made this statement. This man said the uncertainty principle makes the concept of instantaneous frequency impossible. See, uncertainty principle, we have seen it. Uncertainty principle means that when you do frequency analysis, you cannot determine time and the frequency to arbitrary accuracy. Yeah. If you want to define time accurately, then frequency blows up. If you define frequency very accurately, time smears. So the product of del F and del T equals 1/2. That's the uncertainty principle. If we have that uncertainty principle, how can you talk about the instantaneous frequency? Yeah, because the instant cannot be pinned down. What's the noise? Okay. If you cannot pin down the frequency, instance, very precisely, if you pin down the instance, then the frequency smeared. So what is the frequency? It's over a very wide range. So because of this, instantaneous frequency to this day is still controversial. This book actually was published in 2001. Yeah. Now then, if we give up this, how can we define frequency? Yeah. The frequency is not just for fun. It's a very important parameter in data analysis, in communication engineering, in all kinds of applications. So if we look in our textbook defines frequency as 1/T. Yeah. T means period. 1/period is frequency. This definition is very poor. This definition is like asking people what's the velocity. Velocity is distance divided by time. Of course, velocity is distance divided by time. But how long a time? Over how large a distance? That makes a whole lot of differences. Yeah. When you're moving from A to B, if you're moving a constant velocity, you can do this. And then the velocity implies mean velocity. And if your moving is not constant velocity, then the velocity at each instant is different. So the velocity definition should be this. Should be time derivative of the position, not a distance divided by time. A period over T implies frequency defined this way is crude, because one wave, only over one wave you can define frequency. This will work if the wave is sinusoidal wave. I can see wave very clearly. Yeah. But if the wave is not, it's not a simple harmonic, simple sinusoidal wave, and the wave getting longer and longer or shorter and shorter, and each wave distance changing, and this changing is not one wave jump to another wave, jump to another wave. The change is continuous. And then this definition is, the meaning of the definition lost its precise implication. And also, for nonlinear wave, that's another thing. When we say some frequency, we want this frequency to be very meaningful, to be very descriptive. Descriptive. If I have a square wave, I have a sine wave, I have a sawtooth wave, they all have the same period. That means they all have the same frequency. And that is not very descriptive, because if I give you a number, you should be able to immediately know what I'm talking about, what kind of wave I'm talking about, not just a mean period. Yeah. So, not only that, this definition does not even satisfy wave equation. Yeah, we will get back to the wave equation. So then, if 1/T is no good, so what is the definition of frequency? The definition of frequency most commonly appear in Fourier analysis. in wavelet analysis, in Wigner-Weil distribution. They all depend upon frequency. They all describe phenomena in terms of frequency. So in Fourier analysis, it's done by this gentleman, and his work is great. I mean, his work is mathematical point. Yeah, we have mentioned that before. Yeah. How will he describe frequency? He would describe frequency this way. By Fourier analysis, the frequency and the amplitude are all constants, not function of time anymore. Okay, through the through this description, the amplitude and the phase frequency are constant. So time-wise, there's no variation anymore. Amplitude, energy, and frequency are all straight line along this way. Because of that, nobody presented Fourier analysis this way. They all presented Fourier analysis by projection. Projection only in energy frequency space. In other words, just one line, one curve. Yeah. But the Fourier analysis has more problem than that. When we talk about the Fourier spectrum, we're not talking about the Fourier transformation period, not the Fourier transformation of the signal itself. The reason is because of Wiener-Krenschin theory. A pure sine wave is not square integrable. Yeah. If you take a sine wave, you take a square, and the square becomes all positive. The integration from minus infinity to infinity becomes infinity. Fourier theory, Fourier transformation was built upon square integrable. So in order to get a meaningful spectrum, so Wiener-Krenschin said, all right, any signal, when you take a square, probably will not be integrable. Like, for example, a turbulence velocity. A turbulence velocity, when you try to square and integrate, it becomes infinite. However, so if you compute its correlation function, the correlation function decays very fast. Yeah. And that this function is square integrable. So if we do a Fourier transformation on this correlation function, then I will get a spectrum. And that spectrum, it's known as power spectrum or energy spectrum, or what we know, Fourier spectrum. Our Fourier spectrum nowadays are all integral Fourier transformation of correlation function. Therefore, when you integrate the spectrum with respect to all its frequency, what you got is RMS signal. Yeah, this is what we call the energy density. Yeah, so this is the energy spectrum. By the time you do this and eventually get over there, what you find is that, of course, it's limited to linear stationary case. Yeah, and and because it's limited to the linear stationary case, and the spectrum is the mean of the whole property. Not only that, the phase information is totally lost. Yeah. The phase is very important. But the phase information in power spectrum is totally eliminated. Yeah. Let's see the importance of phase. I promised to show you this picture, and I never get a chance to do it. I think this is a good place to show it. Here's a picture of a tire. This is a picture of a little girl. Okay, if we do Fourier transformation, Fourier spectrum, and then we keep the spectrum magnitude here and use the phase over here, what do we got? We get a little girl. And then we keep the magnitude here and change the phase over. Then we get a tire. So what this means is that if we can keep your magnitude, that's what the power spectrum means. Yeah. But I just change the phase. I can totally change, when you reconstruct the picture, you'll never get it back. Yeah. Not only that, this function are totally different. Here, I only use 10 sine waves. Yeah. I can construct this function or a random function. If I use 100, if I use 1,000 components, I will get this as a delta function. This is a white noise. But if we do power spectrum, the power spectrum is the same. Yeah. The reason is that our phase, this phase is random. And when you add this up, you get a white noise, like function. But if I juggle the phase, see this phase? This is a peak. Yeah, here is the peak, but here is trough. This is zero crossing. They're all different phase. But if I make all the phase line up, this is a phase lock. I have all maximum at one location. Then we'll get the delta function. How about the rest of the place? The rest of the place all cancel out because the rest of the place phase are random. Yeah. So we can see that the phase is really, really important. Not only that, I can demonstrate to you that if we change phase, what will we get? For example, we have a signal hello. Yeah. If I scramble the phase, I put the power spectrum. Power spectrum still have phase in there, but we didn't use it. Yeah, because power spectrum, presentation of the power spectrum does not call for phase. If I keep the phase and scramble the phase, randomize it, this is what I will get. Okay, this is what in the mathematical term is a surrogate data. This data and the previous data has the same power spectrum, but different phases. Yeah, and this signal and this signal all have the same power spectrum. Yeah, this power spectrum is original hello, and this is surrogate signal. The spectrum is totally identical. You may say that, oh, when I do hello, I don't do it over the whole span. I will do only little piece. It's the same thing. The little piece, you scramble it, little piece will change. Every piece will change. Yeah, no matter how small you do the little piece. Not only that, this same power spectrum, if I do it a different way, do it instantaneous frequency, do it my way, what happened is that this surrogated signal will give you this IMF by decomposition. And this decomposition will give you this Hilbert spectrum. This Hilbert spectrum compared to look at this. This is almost uniform and uniform noise over there. Yeah. This spectrum is very different from this decomposition and this spectrum. Yeah. This spectrum means my vocal cord, my vocal chamber reverberation, they're all very clear. But if you come to this, they're all different. This, not only that, I can have a very simple signal. This is a nonlinear signal. This is a Duffing wave. Yeah. And if I scramble the Duffing wave, I scramble its phase. What I got this. Yeah. And their spectrum, however, is identical. Yeah. This is where the power spectrum lost its significance, I think. Yeah, because I can have many, many different signals have the same power spectrum. In other words, power spectrum cannot revert back to the signal anymore. Once you get a power spectrum, that's it. Yeah, I want to go back, even though Fourier analysis has inverse transformation, but power spectrum inverse, you lost the phase unless you keep the phase somewhere. Yeah, but power spectrum, nobody keep phase information in power spectrum. Yeah, so once you get a power spectrum, that's it. And this two spectrum, even though it has the same signal, the same power spectrum, if you decompose the surrogate signal, you get this component and this Hilbert spectrum. Yeah. Here you can still see a little bit of what we originally put it in. Yeah. But here it's totally different. Yeah. Now, if we look at the original spectrum, Hilbert spectrum should be look like that. So if you scramble everything, yeah, you still will be able to recover it in Hilbert spectrum. The Hilbert spectrum is based on phase, based on instantaneous frequency. The instantaneous frequency is the derivative phase. So the information is there. Yeah, you can really go back. No problem. So in the previous slides, I have a speaker sign. Actually, when I first made those view graphs, I can hear the sound, but somehow I lost it. Wasn't hooked up with the MATLAB properly. Maybe you people can have a better skill in program. You can do that. The sound will be totally different. Yeah. So, based on, therefore, the Fourier analysis, it's the application and the mathematical foundation is very strict and very limited. Yeah. So, if we want to describe something complicated, something non-stationary, something nonlinear, we should never use Fourier spectrum. But do people care? Most people don't. People just take data and do a Fourier transform, do a FFT, and they get the Fourier spectrum. So here is the Fourier spectrum. The Fourier spectrum, they have many, many different forms. Depends upon the window size you get. You can overcome the non-stationarity to some degree, but then you're limited by the uncertainty principle. So, the uncertainty principle is all because of integral methods. Within an integral limit, the frequency variation is no longer quantifiable. Yeah, it all becomes constant. So integral transformation pair suffers uncertainty principle. Not because uncertainty principle is something intrinsic to the data. It's not. It's because of integral transformation. Yeah, we have mentioned that, and we will repeat that from time to time in this course. All the uncertainty principle burden is because of integral transformation. If we don't use Fourier, if we don't use wavelet, we don't have that problem. Yeah. Okay. So, is there any other way to define frequency? Of course there are. In the dynamic system, frequency is defined by Hamiltonian. Yeah. The Hamiltonian is generalized momentum and generalized coordinate as function of time. So you first define the action. Action is generalized momentum integrated around generalized coordinate. But this has to be, the integration has to be complete one cycle. Yeah. Once you've done that, then partial H with partial A gives you frequency. This sounds nice. The theory is very sophisticated, but this is useless to us because we are doing data analysis. Yeah. The data can come from anything. Yeah. It can come from, of course, a dynamic system like a simple pendulum or complicated pendulum, but it can come from, for example, global warming. It can come from financial market. Yeah. Where's the Hamiltonian for that? You cannot find Hamiltonian. The Hamiltonians so far are definable only for very simple dynamic system. I mean, simple dynamic system means low dimension. Yeah, a few particles. If the particle get more and more, then this becomes unmanageable. So this is not a data analysis method. This is a dynamic method. Then there are other ways to define frequency. Tigger's energy operator, a period between zero crossings. Yeah, this we will discuss. What is Tigger operator? Tigger was trained at MIT, and he was a faculty at MIT. And when he was at MIT, double E department, the department had asked him to look into, I believe is look into the noise characteristic. Yeah, and he said, I don't want to do that. So he quit. He moved across the river, Charles River, to Boston University. And he stayed in Boston University all his life. During his life, during his active period, he's pushing this Tigger energy operator. Nobody paid too much attention, and he died. Luckily, what happened was that he has a very, very powerful relative. His wife's sister married another gentleman by the name of Jim Kaiser. Jim Kaiser is the one defined Kaiser window. See, we have all kinds of window. We have Henning, yeah, Kaiser. Kaiser window is a very popular window. Yeah, Kaiser is a classmate of Tigger at MIT. They are all Wiener's students at MIT. Yeah. Kaiser, after graduate, moved to Bell Lab, and he stayed in Bell Lab to study noise characteristic and devised the Kaiser window. Then, about 10 years ago, he retired. Yeah. I tell you this story. This is an interesting story. How I met them and how this method get revived. And when Tigger died, Kaiser, because his relative, his brother-in-law, so he went to his office, tried to arrange his paper. He left, and then he come across this energy operator. He liked it so much. Jim Kaiser, liked it so much. So he want to publish it. He want to popularize it. And when he popularized it, he find that he himself is, of course, very, very influential. He's from Bell Lab. But he think that he need more people to show power. So he went to MIT, found Tom Quantieri. Yeah. And then he went to Harvard, found Monagos. So three of them, Bell Lab, MIT, Harvard, wrote a two-paper, very long paper, published in the IEEE Transactions. Yeah, talk about Tigger energy operator. I come across Tigger operator. I didn't even pay attention to this paper until Jim Kaiser wrote me, and he said that he liked HHT, but he wanted HHT to be compared with energy operator. Yeah, compare in detail how they look. So that's how I get in touch with this method. Let's see how this method works. This method, this is the energy operator. This is the operator. Any function you put in this operator means you calculate this derivative square minus second derivative times itself, minus second. So anything you put it in there, immediately get derivative 1 take square minus second derivative. This is called the operator. Yeah. In EE, they use operator lots, operational research. In Chinese, called 算子. Yeah. This, what is the meaning? What is the physical meaning of this? If x is position, x squared is velocity. So velocity squared is kinetic energy. Yeah. X double dots means second derivative is acceleration. Yeah. Acceleration is force. Force times distance is potential energy. Yeah. Now, if you have a sine wave, second derivative gives you a negative sign. So if you want to find the sum of kinetic energy and potential energy, you use a minus sign. So this minus sign takes care of the derivative. Yeah. So this actually is the total energy of x, if x is position. So it's kinetic energy times plus potential energy. This is the operator. So if, for example, x equal to a cosine phi, you put it in here, you operate it on, what do you got? You get a squared omega squared. It's very simple. So then Tigger thought, well, if that's the case, now why don't I just also operate on x dot? Operate on velocity. When you operate on velocity, then again, it's x dot second derivative. you get one more frequency out. So the first dot becomes acceleration. Yeah. So you actually get a squared omega fourth. You say, aha, this is good. So I got two different quantity with two unknowns. Yeah, I can solve for a and omega. Omega is what? Is this square, take square, and divided by that. Well, this divided by that, a cancel, omega square, square root, get omega. How I get amplitude? Amplitude is that I put this divided by square root of that. Square root of that is omega cancel that, and a cancel 1, I get amplitude. So look, I can get the frequency, I can get the amplitude by a simple operation. And this simple operation depends only on derivative or second derivative, at most third derivative. So 3 points. This is very, very local. So this frequency is tremendous. This frequency is the most precise instantaneous value. 3 famous signal analysis people in the person of Kaiser, Quantieri, and Manago from Harvard, MIT, and Bell Lab published 2 papers, say how great this is. But you just think, how many times I will, in this operation, what is the basic assumption? Amplitude is constant. Omega is constant. Yeah. If I change a variable, I change omega variable, will you get this? It's totally wrong. Even though they put a almost equal sign or approximate equal sign, the value can be very, very different. It depends upon how amplitude and omega change. Yeah, especially when you have intra-wave frequency modulation. So this energy operator only work for constant amplitude, constant frequency, strictly speaking. How many times you get constant amplitude, constant frequency? If I get constant amplitude and constant frequency signal, do I need to analyze? The answer is no. I know the amplitude already, I know the frequency already. Why should I go through this? Yeah. So, and then the last one is what I call the generalized zero crossing. Zero crossing has been known for many, many years. Yeah. And that is the very simple and more direct way to count frequency. I just count how many times cross zero. Yeah. Then I define frequency that way. However, that's very crude, of course. But when I get this, I decide to generalize it a little bit. Yeah. You don't have to just get the zero crossing. Zero crossing means a control point is very easy to identify. I can get this zero crossing, I can get the distance of this zero crossing. In fact, this zero crossing is one wave, this is only half wave. Yeah. A waveform has many critical points, I call it critical or control point. Zero crossing is obviously one, and the extrema is another one. The wavelength can be defined by the same phase. Yeah. Zero crossing is same phase. Phase cross. When signal cross zero, that means either the imaginary part becomes zero or whatever. This is time derivative equal to zero. Yeah. So those tools, those critical points, either zero crossing or extrema, are very easy to find or to define. So let's identify all these easily defined critical points. Yeah. Once we define this easily critical point, then what we can measure the wave in the following way. The first one is that I will measure the extrema to zero crossing. Zero crossing to extrema. Yeah, extrema to zero crossing and maximum to minimum, zero to maximum, zero to minimum. So in this way, each wave I can measure down to quarter wave. The other example is that I will measure zero crossing to zero crossing, extrema to extrema. So I will measure this, I will skip one. So this distance, I measure half wave. Yeah. The third one is I measure the whole wave, from here to here, from here to here, from minimum to minimum. So that means I will measure this wave, the whole wavelength. So for any point that I pick, here, I have one way to measure the quarter wave. I have two values to measure half wave. I have four values to measure full wave. So all these values are not identical unless this is simple sine wave. Then you ask yourself, which number should I use? Then I submitted that we shouldn't pick anyone. We should determine it by vote. And how to vote it? Just average this value with that with this? That's not fair. This is more local. This is less local. This is the most unlocal. But there are more. So I decide to assign different weight. I assign more weight to this, less weight to that, and least weight to this. So this I assign weight number 4. Even though this one, I give it the weight of 4. This only 2, I give weight 2. This, I give weight 1. So in this average, I will get 4 times weighting factor 4 for T1, weighting factor 2 for T2, weighting factor 1 for that. And then I average it. Once I average, I get a generalized zero crossing frequency. Yeah, this frequency still looks crude, but this frequency is strictly according to the physical definitions 1 over t. Yeah, except this t can be half wave, can be quarter wave. So this frequency is the mean frequency. Any frequency that you define, if the average value does not agree with this, it cannot be right. Yeah, this has to be right because it's the strict definition from physical sense, 1 over t. Yeah. The only problem is the resolution. So now we have many, many different ways to define frequency. Yeah. Now the last Tigger has a super time resolution because it only depends upon second, third derivative, but it's strictly linear stationary processes. Yeah. Generalized zero crossing is robust, but the resolution is down only to quarter wavelength. We have a problem. So finally, we come to HHT. Yeah. HHT gives you variable amplitude, variable phase, so frequency is defined by derivative. Yeah. Then we have also the quadrature method. Instead of using Hilbert transformation, which we will show, actually it's a linear method. When the signal is nonlinear, this doesn't work very well. Yeah. It will give you an approximate solution. In that case, we have to use quadrature method. The quadrature method, there are various ways in the quadrature method. Actually, quadrature method include a lot of variations. What we have to do is we have to normalize x. Take away x is a cosine theta. Yeah, and we normalize x, it becomes cosine theta. Then by definition, 1 minus x is y is sine theta. So sine theta over cosine theta give you tangent, and time derivative of that phase give you the frequency. So now we have 8 different ways. Yeah, except one way it's not a time analysis method. That's the Hamiltonian method. We have 7 different ways. So should we compare this and see how they look? So the frequency instead of 1 over t, 1 over period, now it's become time derivative of phase. So we're going to see. The reason we need that is that we really want to find out this intrawave frequency modulation. Yeah. Another thing we need that is this equation. This equation, everybody knows this equation. This equation is so easy to prove. For any wave function, you have to have a phase function. The phase function is gradually changing. Space derivative that give you wave number, time derivative give you frequency. Cross differentiation equal to 0. It's such a simple equation. Everyone study wave knows about this. Everyone can prove this because this only takes a calculus to prove. Yeah, but nobody pay attention to it. Why? Because if people pay attention to this, people should immediately ask a question: what form will omega and k to be? The omega and k has to be differentiable. Otherwise, why you set up a differential equation? If omega is differentiable, then you ask, will 1 over t work? No. 1 over t is for one wave, it's one value. And if my frequency change at all, the second wave, the omega becomes different. Then your frequency becomes step. Each wave is constant. Jump, step, jump, step. When you put it in here, you get a bunch of delta functions. Right? Every time you jump, the derivative is huge. So 1 over omega won't work. Will Fourier work? No, because Fourier wave number is not a function of space. Fourier frequency is not a function of space or time. They're constant. So when you put it in here, 0 plus 0 equal to 0, it did not exactly violate this differential equation, but it reduced the differential equation to trivial condition. Physics is not study constant frequency. Physics is study frequency variation. Yeah. But if once you use Fourier, when you take any quantity, you represent it in Fourier expansion. When you put it in the differential equation, try to operate, what happened? The frequency never participated in the differentiation because it's 0. It jump out. Yeah, wave number jump out. Never change. So this equation, this simple equation, point to the fact that we have to look for something which is function of time and space and continuously. Only that kind of quantity can faithfully describe the variation of the phenomena. Yeah. So our ideal case for instantaneous frequency is to obtain the analytical signal based on real value functions through Hilbert transformation. Yeah. Then compute instantaneous frequency. This is true only if your data is IMF. Yeah. If it's not IMF, this will not give you meaningful instantaneous frequency. So even if this is IMF, the Hilbert transformation, there are 2 steps. First is the IMF is only a necessary condition. It's not sufficient. Even if the function is IMF, will the Hilbert transformation definitely give you positive frequency? No. Will the IMF give you meaningful physical signal? Still no. Yeah, we'll see that. Okay. So this is the ideal condition. This is the condition when I first used Hilbert transformation. I thought I have already taken a big step to get IMF, but I realized this after I started to play with Tigger's energy operator, because Kaiser insists on looking at each point. So when I start to compute each point, I find a lot of anomalies. So then I start to think, and I eventually solved the problem in almost a year. Yeah, so try to straighten it out. Yeah, this is a Hilbert transformation. Data must be expressed in terms of IMF. Yeah. Traditional application of bandpass is no good. Yeah, we discussed that before. Because all nonlinear signal has a lot of harmonics. You bandpass, you throw away the harmonics, then the signal is useless. But what really make Hilbert transformation problematic is because it's 2. One is Bedrosian theory, the other one is Nuttall theory. Yeah. The Bedrosian theory says that if you have function A cosine theta, and its analytical part may not be A sine theta. See, all we want is A cosine theta, we find A sine theta, right? And if you do Hilbert transformation, you may not get A cosine sine theta. Why not? Bedrosian theory says, look, if I have cosine theta all become sine theta, means A is not participating, right? I do a Hilbert transformation. A never change. I only do it on this. Why A is not changing? A is not changing only if A and cosine theta, their spectrums totally separate, cannot have any overlap. In other words, amplitude has to be so slow and the frequency modulation has to be so high, they have no overlapping. Only in that case, when you do Hilbert transformation, then A cosine theta and A sine theta, the A cosine theta will become A sine theta. That's the first problem, Bajazin theory. Bajazin theory is only page and a half in IEEE transaction. It's been cited maybe thousands of times. Yeah. But immediately after he published this paper, Nato came around. Nato is another one of those MIT Nobel winners student. Yeah. After he graduated, he joined Navy. He's very influential, very good research scientist. But all his research are classified. Most of his stuff people never see. Yeah. Only a few things that appears. Nato theorem is one of that. Yeah. His paper, again, page and a half. Yeah. What he said, he says, hold it. You say that the A and cosine theta have to be totally separate. So how about A disappeared? Yeah, A equal to 1. Yeah. Now, the problem is that is Hilbert transformation of cosine immediately equal to sine theta? He says no. Depends upon theta. If theta is complicated, cosine theta is not sine theta, something totally different. That's Nato theory. Yeah. Then he proceeded to show the difference between cosine theta, Hilbert transformation cosine theta with the sine theta, with the generalized form called the quadrature, which is 90-degree phase shift. This is even more troublesome than that. Right? Here means A and amplitude and phase has to be separate. This means even if I have no amplitude, you still cannot do it. Yeah. So here you can see that from a simple idea of using Hilbert transformation, I get involved and find that Hilbert transformation may not work at all. Yeah. So, for example, this is the this is the voice, and voice look like that. And if I take the voice and do a Hilbert transformation, I take a Hilbert transformation, take a derivative. Look at the instantaneous frequency. Over this range, it may sound okay. Yeah. But look at this. Look at this, all these negative values. So Hilbert transformation applied to this signal directly cannot work. Now, even if we do decomposition, yeah, we still may not work. So this is the more mathematic statement of Bajazin theory. So Hilbert transformation F and G equal to F factor out and H over G, that means applied to cosine theta, if the F and G are totally disjoint. This is Bajazin's theory. And in previous class, I've proved this theory into the class, and I found after I proved it, half of the class fall asleep. So I decided not to do it anymore. If you want it, I can give you the proof. Yeah, but other than that, it's in here. Proceeding of IEEE, 1963. Nato theory. This is Nato theory. Nato theory says that if you have a function, I can find the quadrature. Quadrature, by quadrature's definition, is that all the phase rotate 90 degrees. This is quadrature. Okay, that's the definition. But Hilbert transformation is h x of h. will Qx equal to Hx? No. The Qx and Hx is actually equal to spectrum integrate from -infinity to 0. Yeah. This is Nato theory. Nato is published in 1966. Yeah, in the same journal. I have a chance to see Nato. I really want to meet him because he's such a famous guy. He's a cool guy. This theory is really good. So it happens that the U.S. Navy underwater system command at Connecticut called me, asked me to go up to give a seminar, give a talk. I said, fine, I will come, but on one condition. I have to come on the day that the NATO is there, and I want to talk with him. This is fine. We'll arrange that. Okay. So they pick a day. This NATO will be there, and ask NATO to check a day out. And so I decided to come. A week before I went, NATO had a heart attack. He didn't die. He was in hospital for operation, so I didn't see him. Yeah. So, but this is NATO theory. It's interesting. But NATO theory, I have some criticism for NATO theory. And that's what I really want to see him for. This is a beautiful theory. This pointed out that Hilbert transformation and quadrature are not the same. Right? But this theory is useless to us. The reason is the final answer is defined by Fourier spectrum of quadrature. So what's the difference? The difference is this. What is this? I don't know. If I know the quadrature, I don't have to do this, right? I don't know the quadrature, fine, it's problem solved. Because I don't know the quadrature, and you say the difference is in terms of quadrature, that means the difference is expressed in terms of unknown. Yeah. This is a typical mathematical treatment of something. They prove this is different. But how different it is, I don't know. But it's this. Go ahead and find it. That's one problem. The second problem is that this arrow is expressed from 0 to infinity. Oh, of course, we cannot go in 0 infinity. If we have data 0 to capital T. Yeah. So this arrow is a whole domain. Of all the data domain, I have this much arrow. But that doesn't help me. My instantaneous frequency may be fine everywhere except one location. But how can I find that one location? There's no indication. Yeah. So because of these two limitations, the Nato theory is a beautiful theory. It's really nice. Yeah. It gives us a clear indication what's legal, what's not legal, what's right, what's wrong. Yeah. But it gives us no guidance to locate where it's wrong, how much is wrong at that location. It's wrong is everything. Yeah. So, but I think a mathematician likes this. Sounds great. Yeah. Anyway, so the difficulty of existing limitation, data are not necessary IMF. Yeah. Even if we use EMD to decompose, IMF is necessary but not sufficient condition. Then Bedrosian theory required we do not have strong amplitude modulation, and Nato theory pointed out that the theta has to be very benign, like constant. Yeah, it will work. Okay, so Nato theory is given in terms of quadrature spectrum, which is unknown. That will not really guide us. So here's where we are. We have X. We want a quadrature, which we don't know. So we can only do Hilbert transformation, get analytic. Yeah. But the problem is Hilbert transformation give you analytical function which satisfies Cauchy-Riemann equation. Yeah. Why it does not work? Why Hilbert transformation does not work? Because analytical function, even though it satisfies this differential equation, when you take x squared plus y squared, it does not equal to 1. In other words, the transformation is not a circle. It's a very odd shape. If it's not a circle, and you say that y over x equal to arctangent, you're off. Right? Because of this. What's quadrature? Quadrature is not analytic. Why we should be analytic? Why should I satisfy Riemann-Cauchy theory? I don't care. All I care is that the x squared plus y squared equal to 1. So everything is circle. If it's a circle, y over x by definition is arctangent. Then my theta is correct. Yeah. So this is the difference. We have to go this way, not that way. I don't care about analyticity. I care about quadrature. I care about x squared plus y squared equal to 1. Yeah. So going through all these gyrations, all the variations, I finally down to me that the Hilbert transformation is great, but the Hilbert transformation is not the tool that I need. Yeah. Okay. So the difficulty of Bedrosian theory, just illustrate, yeah. I have a function. This is a sine function. Yeah. A sine function, I multiply a step function. Small amplitude suddenly jump, step function. All right. The frequency should be constant, right? So this is already IMF, sine function multiplied by a step function is symmetric. Yeah. So, but look, sine function spectrum is delta. Step function is this. Yeah. Step function is the integral of delta function. Right? Delta function is white. Integral divided by frequency squared. So it's come down. These two spectrum, this is the envelope spectrum. This is the carrier spectrum. In order for Hilbert transformation to work, carrier spectrum and envelope spectrum should be disjoint based on Bedrosian theory. Should be disjoint. Is this disjoint? This totally cross. So evaluate Bedrosian theory. Look what happened. This is the Hilbert transformation. The lower amplitude is totally off. The higher amplitude is great. This result compares very poor with this. This is wavelet. Yeah. Compare even poor with spectrum. Spectrogram. Spectrogram, even though this block is high, but its frequency is here, frequency is here. Yeah. It compared to Hilbert, look at the oscillation. Yeah. So if we normalize it, all right, the delta function. If I find the delta function, I divide into that, I get a sine wave. A sine wave is no problem. The Hilbert spectrum is constant. This is what we want, but this is not the result because the amplitude information disappeared, get eliminated. Yeah. So that's our problem. Bedrosian theory. So any amplitude change, the Fourier spectrum of the carrier and amplitude probably will not be separable. Most likely it won't. Yeah. I have checked many cases. Seldom I find anything totally separate. A little bit overlap, it's very common. Yeah. Once we cannot separate the envelope, then the Hilbert transformation will not give us the correct phase function, and instantaneous frequency compute through that will have a problem. So I thought of a way. My approach is all engineering approaches. All right, I cannot get amplitude right. I will set amplitude to different place. The amplitude I want, I normalize it. I make the amplitude equal to 1. Yeah. Then the frequency at least is right? So amplitude equal to 1. So we need a method to reduce IMF to be from FM to AM. Yeah. So amplitude give FM decomposition overcome the difficulty of Bedrosian theory. Now my goal is compute frequency, instantaneous frequency. So these are the steps. Let me not talk about steps first. Let's show you what the concrete step. This is IMF already. Yeah. Then this IMF, if I want to do it, normalize it, I take the absolute value. Then I identify all the maximums. Yeah. All the maximum. Then I connect all the maximum with a spline function. Yeah. Then I divide the spline function into the data. Data divided by this spline function. So this is my data. This is my envelope of the absolute value. Yeah. I get F1. If F1 is not good, I will divide it with it again. Yeah. When I divide it with it again, it's x, F equals x E1 divided E2. So x becomes E1 times E2. I can do this many, many times until all the amplitudes is 1. I can always do that. Yeah. So then the Ft then becomes Fn, which is strictly FM signal. What's the amplitude? Amplitude is here. Yeah. So when I do spectrum, it's very easy. I compute the frequency here, I take amplitude here. I still get a very nice Hilbert spectrum. Yeah. Amplitude, frequency, amplitude, frequency, amplitude, frequency. Yeah. So, like for example, this is my original data. The first time I normalize once, I get this red. The red is not 1, sometimes more than 1. Yeah, that's what I cannot tolerate. Yeah, it's many, many points, it's not 1. So I normalize twice, done, everything's fine. Yeah, so then let's see, how's the frequency? This is the signal. If I compute with Hilbert transformation, the green are actually the Hilbert transformation derivative. It's many, many places which is not very good. Yeah, but if I integrate, I normalize it twice, I get the red. Look at the difference. This has a very sharp change. Why we have very sharp change? Anytime you have amplitude small, you have problem. Yeah, amplitude small, you have problem. Amplitude small, you have problem. This is what I run into difficulty when Kaiser challenged me. Says, get a function, compute your instantaneous frequency, and I computed the same way with Tigger's method. Let's compare. And when I compare, I find a lot of this almost single points. Anytime when amplitude is small, because time derivative of the phase of the theta actually is 1 over a squared. When a is small, it's very unstable. Look at this place. Yeah. So normalization really help us a lot. Yeah. And what happened is this, is that originally the phase function looks like this. Amplitude very different. Yeah. When you normalize it, phase function becomes the red. It's near a circle, but it's still not a circle. It's still different. Not only that, this, see the x, the real part is become plus minus 1. The imaginary part can go further than that. And what's the cause of that? This is because x plus y is not 1. If x plus y is 1 circle, this means x plus y is not 1. Means this signal is somewhat nonlinear. Somewhere. Yeah. So the Hilbert transformation cannot take care of that. So so where it's differ from 1, we can spot some place this is 1, some place more than 1, some place less than 1. Where it's different from 1, we compute that. Here, this spot, I have mistake, very large mistake, different from 1. This spot is where the wave has a inflection point. Yeah. This is nonlinear wave. Any nonlinearity immediately give me indication that the instantaneous frequency is wrong. Yeah. This indicator of error is local. It's not global. It's not average. Yeah. Any point that you zero in, the immediate point, you have problem here. You don't have any problem here. This is what we want. Yeah. And this is very easy to compute. The imaginary part plus the real part minus 1 squared. If it's more than 1 or less than 1 squared, even either more or less, you immediately get the indicator of the errors. Yeah. So then the envelope, you can treat it either that way or envelope, you just use the energy for Hilbert transformation, for the Hilbert spectrum. So if you do that, this is an envelope spectrum. This is a wave spectrum. This is an envelope spectrum. So you get FM, AM, 2 spectrums. Yeah. So what is the steps for the normalization? The step for normalization is getting IMF from the data, find the local maximum of the absolute value, flip it over to give it all positive, find the maximum, construct the spline. Yeah, then then normalize the data, use the spline. Data divided by spline. This step can be repeated many times. Then compute instantaneous frequency and absolute value for Hilbert spectrum. The define error. How to define error? Is the AV, is the absolute value minus 1. Yeah, squared. So absolute value can be either positive or negative. Yeah, squared minus 1, squared. So that is the error. So then compute instantaneous frequency from this normalized normalized signal. That's give a tremendous improvement. Yeah. For example, this is the frequency. This is the signal. This signal is a cubic chirp with an exponential decay. Yeah, it looks like this. So this value, when you try to normalize it with the envelope, you can see that here it's already the envelope. You use maximum. The envelope is already cut into the data. You say, how about I use Hilbert transformation? Hilbert transformation envelope is defined by this value. Yeah, this is a Hilbert envelope. This is the envelope of spline. Yeah. So if you use this tool to normalize it, the normalization is not foolproof. Yeah, normalization, again, is approximation. Look at these two normalization. They all have its problem. The problem is that if you use this to normalize, this was the maximum. When you use this to divide into that, this becomes 1. All this becomes more than 1. So the maximum location changed. Right? Now use this to as normalized Hilbert transformation. It's even worse. This would be 1, near 1. But here, you get all kinds of different. So this is the data. This is this is the original amplitude. When you normalize it, it becomes step. So the spectrum, the data, when you divide by this Fourier Hilbert amplitude, the wave get distorted because the normalized curve, it's different. So originally it should be here. It's all skewed. Hilbert transformation amplitude. It's no good. This is Hilbert transformation amplitude. This is the spline. The spline is not good because the peak also shifted, and the value is more than 1. Yeah. So you have to repeat that, and then after you repeat that, you find that the quadrature should be this. Yeah. Normalize this. Before normalize, the phase value is the green, and when you try to compute instantaneous frequency, yeah, if you take the data is already a quote unquote IMF, yeah, because it's cosine function multiplied by an envelope. If you compute the spectrum without normalization, you get this. All kinds of different values. Now, if you use Hilbert transformation to normalize it, you get the green. It's not much improvement. Yeah. If you use the spline to normalize it, you get the red one. The red one is almost covered by others. It's a little bit of wavy lines near the bottom. If you use Tigger's energy operator, it's very nice. See this Tigger energy operator is very nice, except at the beginning it's not very good. So Tigger energy operator sometimes give you good values. Yeah. The generalized zero crossing is the step function. It's the generalized zero crossing is served as my golden standard in the mean, not in the instantaneous value. This is quarter wave. This is quarter wave, quarter wave, quarter wave, quarter wave. Yeah. So any value does not hug along this line, this purple step function cannot be right. Yeah. So the instantaneous frequency here oscillate slightly. That's okay. That's most likely is correct. Yeah. So this gives you all different views, different definition of instantaneous frequency. This is indication that Hilbert spectrum cannot be used. Hilbert transformation cannot be used. And if you use Hilbert transformation to normalize it, also doesn't work. Yeah. If you normalize it, you have to use spline. The formula that we give you is actually the normalized Hilbert spectrum. Yeah, it's already normalized. Yeah. They actually, you have a choice how to normalize it. You can choose different way to normalize it. Yeah, I don't think I can finish all the instantaneous frequency. I want to take a few minutes to explain the homework part. Ms. Liu has put 2 sets of data on the web. Please download this data. Okay, one set, they're not the same length, right? Same length. One is more detailed, and I want you to downsample it and do analysis. First, do analysis with the data we post. Then downsample the data and do EMD and the Hilbert spectrum. And the second set of data is less detailed, right? It's more sparse. Then I want you to upsample this data and then do the EMD and do the instantaneous frequency computations. Okay, that's your homework. Yeah, take the data, do the analysis, then take the first set of data, try to downsample it. Take the second data, try to upsample it. Upsample means using spline to fill the gaps in between. You can fill it 2 points, 1 point in between, 2 points in between, 3 points in between. Do whatever you want. Yeah. Show me what you can do and try to impress me of your work. That's your homework as well as your final examination. I will give you a grade based on your homework you turn in. The deadline for the homework you turn in is the end of December. Yeah. At the end of this year, you have to turn in your homework. December 31st. 30th or 31st. Anyway, all right. Any questions? Tomorrow we'll continue this discuss. Any questions you have? My colleague in Tokyo have any questions? No? All right. If you don't have any question, then the class is dismissed. Thank you very much. Bye-bye. All right. 我们现在可以继续讲。哎呀，这个比那个清楚多了。只是从前那个好像，这个 in fact 这个比我这个 screen 还清楚。啊？它那个 color 怎么会这么 sharp？ 这个什么？
Full HD。
这是 high definition 是吧？
对，
这太好了，这个 OK。他们看不见这个吧？他们看的是这个还是那个？他们应该看的是这个。 传过去的。OK，All right， 你们有没有问题？是。
那个作文篇有讲到那个，应该是 face function 取 gradient 再取那个 partial t 的，然后它的 differential equation 哪一定的那个。
那个 kinematic conservation 啊，等等啊。
它的那个 kinetic。
等等啊。
这个是哥情约是在，就是这个代表的意义。
意义是什么啊？这个代表意义啊，就是这个 wave 不可以 destroy， 我这个 wave 可以变长，但是我 frequency 也要变。wave number 跟 wave number 跟 frequency 它有一个固定的关系。就是说我这个 wave number 要随着时间变的话，我 frequency 一定随着空间也会变。你想我 wave 很简单啊，我跑到一个池塘去啊，丢一个石头进去，丢一个石头，那个石头会有一个 ring 跑出来，对不对？这个 wave 呢是从当中 propagate 出去的。我丢一个石头的时候， 本来池塘是平的，我丢一个石头，这个池塘开始有波浪，对吧？有这个波浪，我这个波浪，它这个 wave 啊，一开始那个 wave 非常短，越走那个越长，所以我的这个 wave number 会变的。
所以这是一种 wave equation。
对，我那 wave number 会变，wave number 会变的话，我 frequency 变不变？这个里面其实这个里面讲的这个还不只是 wave number 变 ，wave number 本来是 spatial 的 change， 这 spatial change 对 time 的 derivative， 跟你 time 的 frequency 对 space 的 derivative， 它的两个就是 space 跟 time 是有关系的啊。那这个是物理，这数学就是嵌入嘛。我先对 space derivative 再对 time derivative， 先对 time derivative 再对 space derivative， 应该是零。这个两个整个做起来叫 kinematic conservation， 就是说我的这个 wave number 可以变，但是你变的话呢，我 wave number 变的时候，就是我这个 wave 变长的时候，我的 frequency 也会变。
这跟 estimated frequency 的，就是
这个 equation， 因为是最 fundamental 的 math， 对不对？我 take a derivative， 我 cross differentiation 它一定是零，对吧？所以这个呢，有这么一个 equation， 这个 equation 被大家认为就是你假如有 wave 的 wave number 跟 frequency 必须 follow 这个，因为这个是最简单的嵌入，对吧？那么假如这样的话，我也不要去讲这个其他的，我只是讲你这个 equation 要成立怎么样？这个 frequency 一定要可以为的，它是 differentiable。假如它 differentiable 的话，它没有 instantaneous value 怎么 differentiate？ 啊，我用的这个主要就是用在这一点。一般做 measurement 的人很少同时给你 wave number 跟 wave frequency 的 information。一般的数据都是给你 frequency。呀，那为什么一般都给 frequency 呢？因为你拿一个 probe 去量出来就是 time series，time series 的 transformation 就是 frequency， 对不对？那么一般得 wave number 什么？假如给你 wave number 的话，这就不会给你 frequency 的。wave number 什么？照一个照片，所以你这个 wave length 一直在变，所以这个 wave length 对时间的变率你也不知道。你要又有时间又有 wave frequency 啊，这个必须要去什么？做个 movie， 对不对？我这个 wave 的 propagate 这个 equation 呢 ，everybody accept， 没有任何人去 proof 过，从实际的 data 去 proof 过。我曾经试过，哎呀，简直没有办法，因为我要得到这个，我必须得到时间空间的数据，就是我要得到一个 movie， 这 movie 怎么去 digitize 它呢？之后就是好了，我说我在 NASA 的时候就说，我摆了30个 probe，30个不同的这个一个摆，对不对？我 probe 跟 probe 之间的变化呢，就是 del x， 对不对？那我时间的变率我完全知道，因为它是 time sequence 嘛，每个 probe 都有 time sequence， 所以我就把这些 probe 统统拿来了，摆了30个，然后量完了以后我真的是 try to prove to verify 这个 theory。算了这个 wave number， 我必须是 differentiate 一次，对不对？因为它是 phase 的 differentiation， 我要再去做这个的时候，我要再 differentiate 一次，2次 differentiation noise 简直出来全都是 noise 加 noise， 根本我没有办法。我到现在为止，我没看到任何一个人用数据去 prove 这个 theory。但这个 theory 是一定是对的，就是必须对的，因为这个 definition 很 clear 的。你要是波动的话，你一定有个 phase 嘛。你的 phase 你 wave number 怎么定 ？kx minus omega t 最简单的 sine wave， 对不对？那么这个理论呢，就是从这里来的，就是我 time derivative 是 frequency，space duration 是 wave number， 这个就变成定义了，这个是 definition， 这个是 definition。OK， 这问题就是说，一般的 wave 的人只有 wave profile， 没有这个 value。啊？谁去找到 phase function？ 找不到。大家都是得到的这个 wave amp 那个 wave 的那个。
像他们在做那个，之前在做那个电磁学的时
候。啊。
电磁波就是这个。
那个电磁波也是波啊，不是 phase 啊。
形式很像这个。
那不是你形式，这我们大家在这个做这个 water wave 的时候也是一样，在 water wave 里面，它那个 equation 是这个 phase velocity potential。
这它有。
对啊，电磁波也是电磁波的 potential。就因为电磁波都是 Laplace equation， 那么你里面有 source 的话，变成那个再加一个 term， 再加一个 source term， 加一个 s， 呀，假如没有 source term 的话是 Laplace equation， 呀，所以那个跟这个不一样啊，那个 phase 跟这个那个是 potential function， 呀，水的 potential 跟电池的 potential， 这个是 phase function， 我用那个小的。我也许应该用 theta， 这样子大家就不会 confuse。下次用 theta， 再用 theta。OK， 还有没有问题？没有问题，我们就下课了。我发掉了。这个 color 怎么我脸真的这么红吗？没有吧。